So at the top of worksheet 18, we actually already did this on a previous worksheet where we had you look at the tangent function as it relates to the unit circle. So the tangent function is, remember, tangent is sine over cosine. So if you think about the unit circle, when you have an ordered pair on the unit circle, which is cosine comma sine, and you think about tangent, that would be taking the y values, as you guys determined them to be y values, divided by the x values. So essentially what you're doing is you're calculating slope. So at 0 radians, whoops, that was supposed to be a straight line, you have a horizontal line which has a slope of 0. So at 0 radians, you have a slope of 0. And then if we, oh, geez. This has not been a good graphing day. I think I'm rusty. What's happening to your slope as our red line segments approach to the next quadrantial? It's getting, yes, it's increasing. It's going steeper, steeper, and steeper. So essentially it's doing this, kind of, until it reaches this quadrantial. Now this is pi over 2 radians. But what is the slope of the line? That was supposed to be vertical. What is the slope of the line that goes straight up vertical? Isn't slope undefined when it's vertical? So at pi over 2, you have an undefined value for a function, which when I graph an undefined value, what that looks like is a vertical asymptote. That was also supposed to be a straight line. This is not going to be a good graphing day. Thank goodness we're graphing all day today. My gosh. Okay, now instead of moving forward through the next period, let's back up. If I look at the unit circle and I go backwards towards what I'm going to call negative pi over 2, because if I measure this direction, I'm going negatively, what's happening to your slopes of these the red line segments as I approach that? They're getting technically smaller. They're getting more and more and more negative. So they're doing this until they reach negative pi over 2, where it becomes completely vertical, which means you have another, what is supposed to be a vertical asymptote at negative pi over 2. So that is kind of what tangent looks like. If you want a better picture of what tangent looks like, it looks like that. I don't graph very well. This is not a surprise. Okay, so a couple things we have to notice about the tangent function. We have to worry about vertical asymptotes all of a sudden. They also have X-intercepts, or midline intercepts, we should probably call them. What is the length of the period? How long does it take the tangent function to cycle through and start repeating? It goes from negative pi over 2 to positive pi over 2. That's a unit of pi. So that's a very key difference between what we have been graphing and what we're going to graph a little bit today, is when you hit a tangent function, the period is pi. Now at the bottom of your formula sheet, there's a little blurb. It looks like this. And it clearly states for you sine, cosine, tangent, a bunch of information about it, and then a very key thing here at the end here is that the period is pi. Now it doesn't mention anything about amplitude. I did trick a couple of you on the amplitude question on last week's test. Remember, amplitude is the absolute value of the a that's in front of the function. Now when I ask you about amplitude on a tangent function, that's kind of a weird question. Technically there is no amplitude. However, you can describe it as having a vertical stretch. This is where, like, because of the nature of the function, it doesn't really make sense. Guys, I don't graph very well. So to claim that my tangent graph has a vertical stretch of 2, and then you come back and tell me, no, it doesn't, we're just going to have a fight about that because I don't graph very well. So it's really hard to see a vertical stretch, especially when you graph like me. I'm just going to trust that you guys know what happens when you have a vertical stretch on functions, okay? But the amplitude technically is not something you have to define for tangent. All right, oh, spoiler alert, it's odd. Why is it odd? Give me the definition of symmetry as to why this is an odd function. It has symmetry of the origin. So with this being the origin, it has symmetry of the origin. Okay. Now I only graphed one cycle. On your test and on your homework, I think they encourage you to graph 2 or more cycles. So if you're like me, you will graph exactly 2 cycles. And you just have to be careful what you're counting by. So we're going to graph some more tangent functions in a moment. Let's flip to, okay, worksheet 19. Look at worksheet 19, kind of halfway, or yeah, about halfway down the page. There's some information here about functions. And then it gives you a little warning about if you're choosing to use your graphing calculator for a little help. On these harder functions, I can understand why you might want to use your graphing calculator to kind of put you in the right direction. But you definitely don't want to depend on it because it is cumbersome, it is slow, and also it doesn't give you radian values in exact form. Okay? So there is one homework question where they want you to use a graphing calculator. For the rest of the homework questions, I would encourage you not to bother with the graphing calculator at all. However, if you are using it, make sure you're in radian mode, and you might try by doing zoom trig before you manually adjust the window after that. Some information. Remember how we kept calculating period as being 2 pi over b? Well, that's not true for all trig functions. That's only true for sine, cosine, and then their reciprocal buddies. If it's tangent, because his period is not normally 2 pi, the tangent formula, and actually everyone's formula, should probably be redefined as this. It's the normal period, whatever that happens to be, divided by b. So for tangent, the normal period is pi. So it's pi divided by b. For sine and cosine, secant and cosecant, it's 2 pi divided by b. You're still going to see the phase shifts, depending on the notation that your book is using. Sometimes they say plus c, sometimes they say minus c. You just have to remember that phase shifts, when in factored form, are just function notation. So, like x minus 2.3 means right 2.3. All right, for funsies, flip back to worksheet 18 now, but look on the back side of worksheet 18. Okay, so big change here. If you're looking at a tangent or a cotangent function, the normal period is pi. So when I look at these 4 problems, I have a sine and a cosine followed by a tangent and a tangent. So they want me to calculate the new period. So this is a sine function. The period is defined as normally 2 pi, but divided by b. Who is b? 3. Very good. Now, I got a follow-up question for you, which it doesn't ask you for, but I'd like you to figure it out anyways. We kept having you guys find what are called quarter points when we were graphing sine and cosine. Because of the nature of the cyclical function, if you graphed quarter points, it gave you all those really awesome points on the quadrancials. I probably should give that a new name today, because when we have the tangent function, I'm not going to be quartering that anymore because there's not 4 significant points on the tangent function. So let's just figure out what we're going to count by. Well, for sine and cosine, or their reciprocals, it's still period divided by 4. So for this question, if you took 2 pi over 3 and you divided by 4, meaning you multiplied by 1/4, what does that reduce to? I heard pi over 6, thank you. So that's a really key idea that I think some of you missed as far as like some of the vocabulary. What you're counting by doesn't necessarily mean like on your axes it's 1 pi over 6, 2 pi over 6. If you have a phase shift, the pi over 6 is what you're adding to move to the next point. You're counting by pi over 6 from where you begin to where you end. Okay. Let's talk about this next graph. It's a cosine. So the period is normally 2 pi, but it's being divided by 5. So that's kind of a weird period length, but just for funsies, let's figure out what we're going to count by. So you take this period of 2 pi over 5, and then a cosine graph would be quartered. So to quarter that, we would multiply by 1/4. So that would reduce to a pi over 10. So I think that's just now that we've looked at our tests, again, we can realize, okay, that's a concept that maybe I missed. And when we test it again, we'll get it. Okay, switch gears though. I'm switching you to tangent function. Normally a tangent has a period of pi. But this tangent function's period has changed because there's a b value of 3. So the period is now p divided by b, so pi over 3. Okay. So that's the period length. Let's talk about what we would count by. If I go back and look at my really crappy graph, actually let's look at a better one. This one wiggle here, this is a single cycle of tangent. So when I'm looking at that and I'm looking for symmetry or any sort of repeating, I'm seeing it's broken into 2 parts. So instead of quarters, this time we're going to be halving it. So when I ask you what are you counting by on a tangent graph, The way you calculate that is you take the period and you divide it by 2. So for us, that would be pi over 3 times 1/2, better known as pi over 6. That counting by number is going to be really crucial to you when you go to graph. All right, and then we have another tangent function. So period is normally a pi for tangent, but it's being divided by 4. So with that in mind, can you guys tell me what we're going to count by for tangent with period of pi over 4? Pi over 8, very good. So you took the pi over 4 and you halved it, which means you're counting by pi over 8. So that's a really crucial, I think, point in our graphing where some of us got a little confused. And I know fractions always add to the fun, guys, but you have a fraction key on your calculator. So if you're worried about the fraction work, just typing the coefficients and hitting math enter is fine. Okay, where are we at now? Worksheet 19A? Why not? Okay. So worksheet 19A, find this problem. It's at the bottom, I believe. So remember, you do have a little bit of guidance on that formula sheet at the bottom if you're trying to figure out what exactly tangent did. Now, if you have a tangent function that is no phase shift, so this one does not have a phase shift here, it is going to go through the origin. There's also no vertical shift. There's 2 things that have happened to it, though. When I throw a negative out in front of any function, what does that do? It's a reflection. Very good. Technically over the x-axis. We'll get to that in a minute. And then a 4 inside the tangent function means that your b value is 4. That means the period length has been adjusted. So the period for tangent is normally what? Pi. But it's being divided by 4. So from beginning to end, the tangent function is a length of pi over 4. However, since I'm going to need to graph, I also need to figure out what I'm going to count by. So to figure out what you're going to count by is you take the period. Now be careful, it's tangent. So how many parts are you dividing it into? 2. So period divided by 2, which would be pi over 8. All right, you are going to count by pi over 8s with me. Good news though, you get to start at 0. It doesn't say, so let's just assume they want like 2 cycles, because on your test it's going to ask you for 2 cycles. As far as marking up the vertical axes, the midline is the only thing you have to mark for me. So since there's no vertical shift, there's like a +0 here. The midline is at 0, so that's where all the intercepts will be located. We already know there's one at 0. The other thing that you need to help me with is figuring out additional intercepts and all the asymptotes. So I know I'm supposed to count by pi over 8. So count with me, children. Pi over 8. What would be 2 pi over 8? Good, pi over 4. For funsies, what's next? 3 pi over 8. And you know what, why not? What's next? Pi over 2, very good. 4 pi over 8 or pi over 2. And then you know what, why not? Let's go backwards. Let's go negative. Negative pi over 8. Negative pi over 4. Negative 3 pi over 8. And I'm going to be out of room. Negative pi over 2. Okay, tangent functions, basically they're going to alternate between x-intercepts and asymptotes. I know this tangent function with no phase shift has an x-intercept at the origin at 0, which means the next thing that I marked is going to be a vertical asymptote. And that goes both directions. So negatively, that one's a vertical asymptote as well. Oh my gosh, that's ugly. So remember, they're going to alternate. So the next thing after the vertical asymptote is going to be another x-intercept. Again, both directions. And then they're going to alternate again. Vertical asymptote next. That is super symmetrical. All right, so this, we have all we need. Now I just have to remember what tangent looks like. Again, you guys have this on your formula sheet for the shape of tangent. However, there's one little thing I forgot about. Wasn't this guy reflected? So normally, don't draw this, but normally the tangent function looks like this. But if I've been reflected, it's going to look like this, which we'll learn in a minute looks like the cotangent function. Okay, once you got one drawn, the rest of them just look like that. It's like a stamp. Here we go. Now hopefully you do oh man, a better job than I do. And things are symmetrical, which clearly mine are not. I would encourage you to use graph paper. I'm going to be honest. I am really stinking proud of my answer key that I'm going to post today for your homework assignment. They look beautiful. And the key to my success was graph paper. So, there we go. All right, guys. So tangent's weird. It's a new function. It has new attributes. We got to think about it. Let's talk about this one. So Hofbauer gave us a little graphing calculator assistance so you can see what it looks like in the graphing calculator. Unfortunately, nothing's labeled, and if I want to go find points, I'd find some really ugly points that aren't going to help me any. So I still have to know how to do all this without the graphing calculator. Plus, time-wise, not effective to use your graphing calculator when you're testing. So -5 is a vertical shift. For some reason, they wrote it in the front. If that bothers you, write it off to the side like this. That means we have a vertical shift of down 5. This time, I need you to carefully count out where your midline is, which is now at -5. And of course label it. So a few things have happened to this tangent function. Again, we have a reflection. There's a 2 that's in front of the tangent function this time, which means it's been stretched vertically. But like I said, I graph really cruddy, so you're not going to see that on my graph. You're just going to have to use your imagination. But if you look at this screen that Mrs. Hofbauer took a screenshot of, she showed the difference between just a regular tangent function versus a stretch of 2. There is definitely a difference. It goes up faster. I don't graph well enough to notice the difference, so I don't bother. Okay? As long as you know that there's a vertical stretch, we'll call it good. All right, here we go. I need to figure out period, I need to figure out what I'm counting by, and then I need to label some stuff. So tangent function, this time there's no b value besides a 1, so nothing's going to get affected. So the period for tangent is pi. And for tangent, you cut them in half to count, so you're going to count by pi over 2's. Now I'm going to do all my labeling on the x-axis. But that's not where the x-intercepts are going to occur. It's actually a midline intercept. We'll get to that in a minute. So tangent goes through 0. This one has not been phase shifted, so it will go through 0 as well. Well, down here at -5. Let's count by pi over 2's. 1 pi over 2. 2 pi over 2, which is pi. 3 pi over 2. I'm going to stop counting. Let's go backwards. -pi over 2. -pi. -3 pi over 2. So I have a tangent. Has not been phase shifted. So the very first mark that we make that normally goes through the origin is kind of going through the origin, except remember everything's down here at -5. So the first midline intercept happens right here at 0. The next thing you marked up for me, remember it toggles between intercepts and asymptotes. The next thing you marked up for me is a vertical asymptote. In both directions. The next thing you marked for me is a midline intercept. Yeah, you know what I do here is I mark it on the axes, and I do it every time, and I'm so proud I haven't done it yet today. All right, and then the next one after that is another vertical asymptote. Okay, so there should be a little symmetry if you can actually draw well. And then I'm going to forget, so remind me that this has been reflected. So remember, instead of a normal tangent-looking graph, you have a reflected version of that, so it looks like this. Which is not at all what the calculator shows, but you know. Oh man. You do want to mind the asymptotes. Try not to graph sloppy like I just did. Stay within your boundaries. It will also ask you on, I don't know about the homework, but I know on your test it's going to say identify some ordered pairs that it went through. So the ordered pairs that are easiest to identify without using any calculator would be all of these midline intercepts. So You know, at 0, -5, at negative pi, -5. Those are the easy ones to identify. So when I ask you for tangent, I'm not going to ask you to identify a bunch of points. I'll probably ask you for 2. All right. Where do they want us to go now? All right, back to worksheet 18. Let's talk about our reciprocal buddies to our original sine and cosine graph. So cosecant is the reciprocal to whom? Sine. So if I think about math and taking the reciprocal, we know that means to flip a fraction around essentially. So here's what's going to happen. You are going to ghost in the cosine or the sine function. So you're going to pretend like the function is actually sine or cosine, depending on what the question is. So if it's secant, it's cosine. If it's cosecant, it's sine. So they've already done that part for you. It looks like I drew it, but I didn't. So that's the ghost in of a sine function. Then the next thing you're going to do is identify, you're going to switch x-intercepts to asymptotes. So zeros become asymptotes. Think about that, guys. When you take a fraction that's equal to 0 and you flip it around, what does it become? Undefined. So on graphs, undefined values become asymptotes. So all of these x-intercepts, all of these zeros that you see, are now going to become vertical asymptotes. All right. Then you're going to identify any maxes and mins from your ghost function. And I'm going to use the very unofficial term of horseshoe, but then you're going to make a horseshoe. I don't mind graphing these, because even I can make them look halfway decent. So this guy right here, the maximum value at the top of this sine function, is going to become the bottom of this particular horseshoe. So just kind of stay within your boundary. Oh my. It just went and bragged about how good I am at graphing these, and look what I do. All right, there you go, horseshoe. This minimum, that's going to be the top of this horseshoe. So the extreme, oh man. The extrema are going to match up. Now the reason we're getting this weird horseshoe shape, this horseshoe effect, is because if you think about the ordered pairs that are along the ghosted sine function, if you were to take this ordered pair and come up with the reciprocal, instead of approaching back down to 0, they're going to go off to infinity. If you think about taking reciprocals of numbers and fractions, that's what happens. So they're going to go up without bound along the vertical asymptotes. So you get this weird shape. What I just graphed in green is actually the cosecant function. Everything else we graphed was just to help us get that green part. So let's take a, that's what it's supposed to look like, by the way. I didn't do a very good job. What's new? All right, let's talk about secant. What's secant the reciprocal of? Cosine. So same steps. You're still going to ghost in the cosine function. You're going to say all of your x-intercepts become vertical asymptotes. So all of these x-intercepts are now vertical asymptotes. And then you identify all of the extrema, or the maxes and mins, and you create this horseshoe effect. Oh man. So ugly. Okay. Mine end up looking like parabolas. They're not. They're not supposed to look like that at all, in fact, but that's what mine look like. So some kids are looking at this going, I don't really see a difference between secant and cosecant. There's definitely a difference. It has to do with where their maximums occur. And it's just like with sine and cosine. One could argue a sine and a cosine graph are really the same thing. One's just been shifted over by a partial period. Same thing with secant and cosecant. They are the same shape. They've just been shifted over a bit, right? All right, so let's see some examples. Oh, cotangent. Got to talk about him. Same thing, guys. I'm going to say you're going to ghost in the tangent function, but you just learned tangent. So it's not really like something that rolls off the top of the head. But again, it's on your formula sheet. So remember, if you forget what it looks like, you can always revert back to your formula sheet. Same idea, guys. All the X-Intercepts become vertical asymptotes. So you got a vertical asymptote occurring here, here, and here. Now, on the flip side of that, what happens if you flip a fraction that's undefined? It becomes 0. So where you used to have a vertical asymptote, what you're going to have now is an x or a midline intercept. So all of these vertical asymptotes are going to become midline intercepts. So that reciprocal action works both ways. Zeros become undefined, but undefined becomes a 0. And then I really hate graphing cotangent. I don't know why. I think I just don't like tangent, and there's snowballs from there. So I have to remember that cotangent, you got to live within the boundary lines you drew, right? And cotangent goes the other direction. It looks like a reflected tangent. There we go. Yeah, I've done worse. Okay, so that's 2 cycles, and we'll call it good enough. So you're going to be graphing unusual graphs today. That's the moral of the story. Let's look at some more examples. Where do they want you flipping now? Worksheet. No, not 19. Okay. Bottom of worksheet 18A, apparently. Bottom of worksheet 18A. They want you to graph 2 times the secant of 3x. But we're actually not going to start with that function. We're going to start by ghosting in what function? 2 times the cosine of 3x. Very good. So all the stuff that you did when you graphed cosine is still going to show up today. This is the start of us graphing secant. So you have an amplitude of 2. Now don't go crazy with these amplitude lines, guys. There's no vertical shift, so midline is still at 0. Your max line is going to be at 2, and your minimum line is at -2. The reason I don't want you to make them like super large is because you're going to have to graph above and below these max and min lines in a minute, so don't make it too huge. Now it will ask you to graph 2 periods. So let's talk about what the period length is. For cosine, we know the period is calculated as normally a 2 pi, but it's being divided by b. So your b value in this problem is a 3. That's great, except that doesn't help me label anything. So instead of calling them quarter points today, let's just say, what are we going to count by? So cosine is the type of function that cycles every 4 quarters, right? So we divide by 4. So take the period, 2 pi over 3, and divide it by 4, or multiply by 1/4. So we are going to count by pi over 6. Thank you. All right, there's no phase shift. That's good news. So I'm going to call 0 our starting spot. And I'm going to count by pi over 6's. I might encourage you to count both positive and negatively, since you have to go to 2 cycles. So 1 pi over 6, 2 pi over 6, better known as pi over 3, 3 pi over 6, which is pi over 2, and then 4 pi over 6, which is 2 pi over 3. And then instead of keep going forward that way, let's back up to negative pi over 6. And then another negative pi over 3, negative pi over 2. Oh boy. And then negative 2 pi over 3. So, we haven't actually talked about secant yet. We're still in cosine land. I'm going to ghost in, this is not actually my function, I'm going to ghost in the cosine function, which starts where? 0, 2. And then every marking that I counted by would continue on, and you would ghost in this lovely cosine function. So there's one cycle of cosine. Let's back up and get the other cycle. That went a little vertical or horizontal, sorry. Okay, what we just graphed is not at all what we want. So we have to think about our little checklist. We just ghosted in the function, the cosine function. Now I need to change all of my midline intercepts to what? All these intercepts get changed to vertical asymptotes. So I usually use a highlighter, or at the very least I just dash a line in, but you need to see this vertical asymptote boundary because it's going to help you graph in a minute. And then all of your extremas become the top or bottom of the horseshoe portion of the graph. Here we go. So like this maximum is this guy. This minimum helps you with that one. This maximum, right there. Minimum. And I went a little overboard here. I have more than 2 cycles, but that's okay. In order to graph 2 cycles of a secant or a cosecant, you need to be looking for 4 horseshoe shapes. Okay, so I went a little extra. That's okay. I'm also going to ask you to label ordered pairs. What do you think would be super awesome ordered pairs to come up with? Yeah, all these things right here, right? These extremas. So without using any sort of graphing calculator, I can tell you all those ordered pairs really quickly because I have everything labeled. So like this guy is 0, 2, excuse me. This is pi over 3, -2, and so on and so on. So when I ask you to, it's just Walgreens. You got excited. You're like, they canceled school. They didn't cancel school. Yeah. So all those extrema are going to be the ordered pairs that I want you to list out. Don't go crazy and give me some weird ordered pairs off your calculator. That's a waste of your time. Oh boy. Now you're on 18B. And then just to really mess with you, they're like, oh, and you know what? I think we were going to graph a tangent. Okay, sure. So, I know your first thing out of your head is like, oh, the amplitude is 3, but remember for tangent functions and cotangent functions, the amplitude's not a defined value. The 3 is actually a vertical stretch. I don't really care for you to notate that on your graph. Just remember it's going to go up faster than normal. I wish you all the best. All right, let's talk about tangent though. The tangent, the normal period for tangent is what? Pi, except we have a b value who's going to be changing the tangent because we're going to divide by 4 pi. So this period is calculated as 1/4. So the entire length of your tangent function is going to begin and end in a unit of 1/4. So when I think about what I'm going to count by, how many sections do I break tangent into? Into halves, yes. So into 2 sections. So we're going to count by 1/8. And then the only thing I have to remember is where does tangent start? So if I forgot, I would go look at my formula sheet, but tangent is the function that starts at the origin. Cool. And then it's just count by 1/8. Well, this is nice. Look what they did for you. They already counted by 1/8. Okay, so remember, tangent alternates between midline intercepts and asymptotes. So if this first one is a midline intercept, this next one is an asymptote. And that works backwards as well. And then they keep alternating. So the next one is a midline intercept, followed by an asymptote. And it does say, well, it doesn't say anything. It just says label 2 points. So I'm going to be able to come up with 2 points at this point, so I'm going to stop. All right, what's tangent look like again? If you're not sure, you go and revert back to your formula sheet. Tangent, and this one time, it's not reflected this time. So tangent is the one that goes like so. Oh, that was pretty good. That wasn't. Okay, so there's 2 cycles of tangent. Hey, just something to point out, guys, because some of you struggled with this on the modeling. The period length is from beginning to end, right? It goes from -1/8 to +1/8. That is a period of 1/4. It's the time on modeling, but the distance on the x-axis for when a cycle begins and ends. It's measuring, okay, measuring. And those ordered pairs that we didn't really identify, but we sure could, they were at, there's one at 0, 0, and this one's at 1/4, 0. So the easiest points to identify on tangent and on cotangent are those midline intercepts. Oh boy, that one looks fun. Okay, so we are not going to graph cosecant yet. First, we're going to talk about ghosting in which function. Who's the buddy for cosecant? Sine, yeah. So we're really going to ghost in 3 sine of 2x, and then we'll adjust everything from there. So the amplitude is 3. So you have a midline shift of nothing. So midline's at 0. Amplitude is 3. I do need to calculate the period. This one does not have a normal period of 2 pi. So it's 2 pi divided by 2. So the period length for an entire sine curve is going to be pi. But think again, sine is broken up into how many parts? 4. So you're going to count by the period divided by 4. All right, there's no phase shift on this question. So starting at 0, I need you to count by pi over 4s. I need you to get 2 cycles in here somehow. They didn't leave me a whole ton of room to go negative, so it's up to you. You can either count 2 cycles forwards or 1 cycle back and 1 cycle forward. I'm just going to start counting. All right, pi over 4, and then 2 pi over 4 is pi over 2. 3 pi over 4. And 4 pi over 4 is pi. Now, again, you can keep going forward, or if you'd like, you could back up, because it's pretty easy to go negative at this point. So negative pi over 4, negative pi over 2, negative 3 pi over 4. I should have wrote smaller. Here, back up. Negative pi. So I'm going to ghost in sine, which starts at middle, 0. But this isn't actually the graph. All right. But the good news is that was the hardest part of the question. So once you have the sine function ghosted in, now I have to remember to switch all of my midline intercepts, or my zeros, to asymptotes. So all of these intercepts are going to switch to vertical asymptotes. I really encourage the use of highlighters when you're doing this homework. And then all of your extremas become the extremas for the horseshoe parts. So like this maximum helps you with that horseshoe. This minimum gives you that one. Oh man, that's crooked. Okay, this maximum gives you that guy. And then here we got a minimum. Whew. All right, so it's just going to be more of that, and we can, when we come back and see each other on probably Friday, we can look at some more notes questions. I will warn you, the very first question on your homework has a phase shift. So let me just kind of talk you through that real quick, because none of these examples have phase shifts. Number 2 is a tangent function. It doesn't change the period. There's no b value other than 1, but it does have a plus pi over 4 unit. Which, talk to me about what does that phase shift mean? Left, thank you. So it's been shifted left pi over 4. We have to kind of keep that in mind. The period for this question, it's tangent, so the normal period is pi. There's no b value that's going to change it, so go ahead and count it pi. But what do we count by? Pi over 2. Very good, because tangent gets cut in halves. So here's where I think some of you struggled on the phase shifting on your last test. I know that my first mark that I have to mark down is going to be counted at negative pi over 4 because of the left shift. The way you get to the next point is you either add or subtract this number. So to move this way, you're going to add pi over 2. To move that way, you're going to subtract pi over 2. So if you're really afraid of the fractions, just type the coefficients on your calculator, guys, but this one's not too bad. You can call this 2 pi over 4, right? So negative pi over 4 plus 2 pi over 4 is 1 pi over 4. Negative pi over 4 minus 2 pi over 4 is negative 3 pi over 4. So that's how you get along the axes. You're just adding and subtracting your counting numbers. We used to call them quarter points, but we can't call them quarter points anymore today. Okay? I think the fractions freaked something out. I think is what happened. So we're going to see more of that in the next test, of course. And you got a little book assignment. All right, you got 2 days to make it happen. I might suggest you go visit Mrs. Hoffbauer's remediation bin for some remediation papers before you leave today.